Starting from this video, we shall explore how we can arrive at the concept of Lebesgue integration from that of Riemann integration. So first let us recall what Riemann integration does. Suppose I have a function which I shall call f defined over a closed bounded interval ab. The function is non-negative above the x-axis and is bounded from above by some value which I have denoted by capital M. Now our aim is to be able to find out the area under the curve. Now for this, the Riemann integration approach is like this. You take any arbitrary partition of the domain. They need not be equal, but there must be finitely many subintervals into which you have partitioned the domain. Then on each subinterval you raise a rectangle until it hits the graph. For instance, over this subinterval I have raised it and I cannot raise it any further without crossing the curve. Now here also we shall raise one rectangle and similarly over the other intervals as well. Now we have a finite collection of rectangles. We know how to find out area of rectangles. So we can say that the total area of all the rectangles, that must give you a lower bound for the area that we are trying to find out. We still do not know what is the area under the curve, but at least we know if it is some number, that number must be greater than or equal to the total area of all these rectangles, and that is a quantity which we can always work out because the area of a rectangle is this width times the height. Next, Riemann did a very similar thing, but now he started from the top bound, something like the ceiling, and he brought it down, and as a result he get another set of rectangles that I am showing by dashed lines. In this case I am bringing it down until it just hits the curve, it just falls below the curve. Similarly from here it will be this, over here it will be something like this, and similarly it should be like this over the other intervals. So now I get another set of rectangles. I am always measuring all rectangles starting from the x-axis going on up to the dashed lines. So I get another set of rectangles whose areas must be greater than or equal to the area under the curve. So even though I do not still know what is the area under the curve, I have got an upper bound of that and a lower bound of that, and just by looking at the picture it seems quite reasonable to claim that if I make my partitions finer and finer and take all possible partitions, then I can come arbitrarily close to this curve, and this led Riemann to define his integration in the following way. Let script D denote the set of all non-negative step functions with finitely many steps, and my functions are all defined on the closed interval a to b. This is just a notation so that I do not have to say every time step function finitely many steps. Then what he was doing is he was first approximating it from below, which means he took a function little s in script D, that is this function, step function, which is less than or equal to f, so it is under the curve, and he took the area of that s. So this area s is precisely this shaded region. He will take the set of all such areas that you can take, whatever simple function or whatever step function you take with finitely many steps below the curve, and he will try to approximate it as much as possible. Since he is doing it from below, he will take supremum as close as he can get. Similarly, he will take another set of step functions which will try to approximate it from above using this notation. That will be area of S, but this time S is greater than or equal to F, and of course we are considering only step functions with finitely many steps. This time I am trying to bring it as much down as possible, so I will take inf, and it's only natural just by looking at it intuitively that if these two areas are the same, in that case that common value should be called the area under the curve of F and denoted by F Tx A to P. Now, while that was a brilliant idea, trouble arose with this condition. One thing is certain, that this supremum is bound to be less than or equal to this infimum, because these are all below the curve and these are all above the curve, and intuitively it seems that they should be always equal, but unfortunately there are situations where strict inequality prevails. And for those functions for which you do not have equality, we call them that they are not Riemann integrable, so for them this does not exist. Now that caused a lot of problem, because how to check whether given a function such a function is Riemann integrable or not, and that led many mathematicians to try to massage the theory of Riemann into some way which is more manageable. And Lebesgue was trying to do precisely the same thing when he had a brilliant idea which eliminates this problem to a great extent. And that's what we shall discuss in the next video. In this exercise, I am giving you the graph of a function f, non-negative, bounded. This is my function, and at this particular point it has a little discontinuity. The point has moved over here, and I have also given you one partition. Your job is to actually draw, not mathematically but using just your graphical skills, the lower set of rectangles as well as the upper set of rectangles.